Okay, so let's suppose we're given an equation of the form y equals the indefinite integral of f of x dx. Okay, another way we could write this is y equals, and we'll use big F of x to represent the antiderivative. So big F prime equals f of x. That's sort of a way of thinking about the antiderivative. And big F of x plus c. Okay, we can't forget the c. Very important. Um, so when we write an equation of this form, okay, we're going to call that the general solution to a differential equation. Okay, the general solution. Okay, that's always of the form plus c, right? Because hopefully you did the quick reading of your notes packet, and that talked about how changing the little constant, okay, all that does is it shifts your antiderivative up and down. Okay, it's a vertical shift. Um, so let's look at an example. All right, we'll do a couple examples where we find a general solution, and we'll use an initial condition to find a particular solution. So find the general solution to the equation f of x is equal to the indefinite integral of 6x dx. And then we'll find our particular solution, satisfying f of 0 equals 8. Okay, so first things first, let's take our antiderivative. So f of x, power rule says add 1 to the exponent and divide by 2. Can't forget plus c. Okay, we'll simplify that just a little bit. So f of x is equal to 3x squared plus c. Okay, so that's our general solution. We did that in this nice blue color. Okay, we'll do the particular solution, this reddish, orangish, pinkish shade. Okay, so our particular solution, we need the initial condition that f of 0 is equal to 8. And what that means is when x is 0, f of x is 8. So we'll write 8 is equal to 3 times 0 squared plus c. Okay, so we have 8 equals, well, that goes to 0. 8 equals c. So our particular solution in this case is f of x is equal to 3x squared plus 8. Okay, and that's it. That's all we have to do. Okay, let's do another one. So find the general solution. This time, and we'll go back to blue. So this time, our f of x is the integral of 3x squared dx. Okay, so indefinite integral, again, power rule, going to skip a step here. Increase the exponent by 1, divide by new exponent, should cancel out to x cubed. Okay, plus c. Can't forget the plus c. All right, so there's our general solution. Pretty easy. I mean, you've done this stuff before. Okay, this shouldn't look like anything new just yet. Okay, up next, so we have the initial condition that f of 2 is equal to -3. So plug 2 in for x and -3 in for f of x. So we'll say -3 is equal to 2 cubed plus c. Okay, -3 is 2 cubed plus c. All right, let's go ahead and solve for c. So we have -3 is equal to 8 plus c, subtract your 8, so you get -11 is equal to c. Okay, hopefully this doesn't feel like anything new just yet. Okay, we're going to change things up a little bit notation wise, but essentially it's going to remain the same. Okay, so x cubed, let's see, minus 11. All right, so there's our particular solution. Okay. Go ahead, pause the video, take a moment to read the next section of the notes on differential equations. Okay. So hopefully you read that section. We're going to go ahead and draw a little dividing line here. So whenever we write something of the form, like this, dy dx is equal to, and for example, x cubed over y, we call this a differential equation, okay? Where you have a derivative on one side and a mixture of x's and y's on the other, okay? You're lucky if there are no y's, but sometimes there are, okay? Since the highest derivative in this example is the first derivative, we would call this a first order differential equation, okay? Now in AB, we're really only going to mess around with first order differential equations. I can't think of any examples off the top of my head where we'll do second order, but that's definitely something that you'll see in college. Okay, so solving them is pretty straightforward, and I want you to take a moment, again, just read through the notes real quick, pause the video, and read through the notes up to the steps for solving differential equations. Okay. And I'm going to go ahead and copy these steps here for you. So let's copy this. We'll paste it in here. And that looks like a good spot for it. Okay, so, and we're going to actually make a better way of writing these steps as well. So we'll start with this. Everything is very explicit, okay? And we'll start with an example as well. So here's our example. We'll do example 3. Okay. So example 3, we have dy dx is equal to sine of x. And here's our initial condition here. So let's see, step 1, move everything with a y to the left, including dy, and everything with an x to the right. So no y's on the right side, so we just have to move this dx over. Let's go ahead and do that. So we can do it by multiplying sine of x dx. Okay, so step 1 is done. Okay. Step 2, integrate both sides and add plus c to the x side. So we're going to go ahead and step 2, we're going to take the indefinite integral of both sides. Okay, and remember there's a 1 in front of this dy, right? So the antiderivative of 1 dy, that's just y, okay? And the antiderivative of sine, well, what do we take the derivative of to get sine? So the derivative of cosine is negative sine. So our antiderivative, we're going to need an extra negative out there, negative cosine of x. Now, we only add a plus c to the x side. Now, why is that? If we put a constant on the other side, we would end up moving it over anyway. So we're not really going to worry about the constant on the left side. Okay, we'll just put it on the right side. So step 2, we're done. Okay, and this is our general solution. Here's our general solution. Okay. Now, if we want a particular solution, we have to go a little further. So we're given a point, y of 0 equals 2. So we'll plug that in and we'll solve for y. I'm sorry, solve for c. Okay. So let's see, we have y of 0 is equal to 2. So when x is 0, y is 2. So we say 2 is equal to negative cosine of 0 plus c. Okay, we've practiced our sines and cosines enough, right? So cosine of 0, we know that's 1, so negative cosine of 0 will be negative 1 plus c. Okay, get the c by itself, so we'll add 1 to both sides. We have 3 is equal to c. Awesome. And we'll substitute that back in. So we have y is equal to negative cosine of x plus 3. And that's our particular solution. Okay, solve the equation for y. Everything's in terms of y, so we're good to go there. Okay, good to go. All right, we're going to do 3 more examples. So if you need to catch up, I'm about to scroll down, so take a moment and pause and make sure you've got everything copied. Okay. So let's look at another example here, and we'll put another line across. That's straight enough, right? And let's look at example 4. Okay, so example 4. This is not written as a dy dx, but it's still something that we can do. Should be pretty straightforward. So here we go. The acceleration of a body moving along a coordinate line can be modeled by the function a of t is equal to cosine of t. Okay, and we want to find the velocity and the position functions. Okay, we're given initial conditions for velocity and for position. So let's go ahead and write that down. So we know that acceleration is the derivative of velocity. So if we take that backwards, we know that velocity is the antiderivative of acceleration, or the indefinite integral of acceleration. We can think of those as sort of the same thing. Okay. So we know that a of t is cosine of t, so we'll plug that in. Cosine of t dt. Okay, antiderivative of cosine, well, we take the derivative of sine to get cosine, so sine of t plus c. Okay, so thinking about our steps, we didn't really have to do step 1 because it wasn't written in this Leibniz form. Okay, so we just had to start at step 2. We integrated. Okay. So we have, here's our general solution, and we want the velocity function, so what we're going to need to do is use our initial condition that v of 0 is equal to negative 1. Okay, so v is negative 1 when is 0. Sine of 0 plus c. Okay, so sine of 0, again, we should know this by now, is 0, so negative 1 is equal to c. Okay, so if we write out our velocity function, filling in for c, we get v of t is equal to sine of t minus 1. Okay, so we did velocity. Now let's do position, and we'll do that in this nice pinkish color. Okay, so just like we know that acceleration is the derivative of velocity, we know that velocity is the derivative of position. So working backwards, we can think of position as the antiderivative of velocity with respect to time. Okay, well, we just found v of t, so we'll plug that in. S of t is equal to the antiderivative indefinite integral of sine of t minus 1 dt. Okay, so let's see, we just did this before, right? So the antiderivative of sine we said was negative cosine, so we have negative cosine of t minus, and What does this go to? This goes to t. Okay, thank you, power rule. Okay. Oh, and we can't forget our plus c, right? Can't forget plus c. It's the most common mistake made in this area is forgetting the plus c. Remember, you don't get full points if you forget your plus c. Okay, we'll use our initial condition, s of 0 equals 1, to solve for c. So s of 0 equals 1. So 1 is equal to, let's see, negative cosine of 0 plus c. Okay, plug in 0, we get 1 is equal to, we did this before, negative cosine of 0, negative 1 plus c. Okay, solve for c, we get positive 2 is equal to c. So our position equation, s of t, is equal to negative cosine of t minus t plus 2. Okay, let's take a second. Let's look at example 5. We'll put a little line here again, same blue color. Okay. Okay, so this time we're given something in Leibniz form. So we're going to use our steps again, and I'll copy those back down here just so we don't have to keep scrolling. I know that's kind of annoying, so we'll copy these back down here. Okay. So let's see, let's rewrite. Never a bad idea to rewrite. So we have dy dx is equal to e to the x, and this is going to look kind of gross, but you know um, when we do it, it's not that bad. 20 times 1 plus x squared all raised to the negative 1. Okay. Now, before I even go any further, what I would do is I would simplify this, right? I don't like negative exponents. Not a huge fan, so let's just go ahead. We're going to simplify this real quick. So we have e to the x plus 20 over 1 plus x squared. Hopefully, you're seeing something familiar. Okay, make that look more like an e there. Okay. So step 1, move everything y to the left. Okay, we're good there. And everything x to the right. So we'll bring the dx up. That's always a step that has to happen. E to the x plus 20 over 1 plus x squared dx. Okay, step 1, done. Okay, step 2, integrate both sides and add plus c to the x side. So we're going to integrate both sides. Okay, so the integral of 1 dy, we get y. Remember, we don't need the plus c. We're just putting all the constants on the right side. Well, the integral of e to the x, that should be pretty easy, right? Nothing happens there. Now, this 20 over 1 plus x squared, let's think about that for a moment. So we have 20 times 1 over 1 plus x squared. Can you do u substitution here? No. If you do, then let's say we choose u equals 1 plus x squared. All right. When we find du and we try to substitute, we're going to end up with more x terms than we started with. Nothing's going to cancel. So hopefully maybe we think about some other functions and their derivatives, and we see that, hey, the derivative of inverse tangent is 1 over 1 plus x squared. So our antiderivative of 1 over 1 plus x squared is inverse tangent. Okay, and there's a 20 out there. It's not a big deal. Constant comes along for the ride. Okay, or you can write it arctan, if you want to write it like that. Go ahead. Nobody's stopping you. All right, plus c. Don't forget your plus c. Okay, now let's see. We're given a point. Plug in the point and solve for c. Okay, well, we were given the point that y of 0 is equal to -2. Okay, y of 0 is equal to -2. And you might already be sweating because you have to plug something into inverse tangent, but it's not that bad. So we know y is 2, -2, when x is 0, so e to the 0 plus 20 inverse tan of 0 plus c. So let's think inverse tan for a second, and I think the unit circle helps here. So we'll make a straight line, straight-ish, straight-ish, unit circle. Let's pretend that's a circle. So in order for inverse to plug 0 into inverse tangent, we have to think about tangent of what is 0. That's how we think about inverse tan. So, well, tangent is sine over cosine, right? Sine over cosine, theta, theta, can't forget our thetas. And on the unit circle, the sines are the y values and the cosines are the x values. So tangent is y over x. So where does y over x give us 0? It's wherever y is 0. So it's at 0, 1. Oops, 1, 0. I'm sorry. 1, 0. And -1, 0. Okay. Well, if we just think about going from 0 to pi over 2, then that's enough. So we can think of inverse tan of 0 as the angle 0. Okay, so we have -2 is equal to anything to the 0 power except 0 is 1 plus 20 times 0 plus c. Okay, so we know that goes away. We have -2 equals 1 plus c. So -3 must be equal to c. Okay, so in order to write our particular solution, we're just going to plug our -3 in for c. Okay, and that's it. We don't have to solve for y. It's already by itself. Okay, already by itself. Take a break, take a pause, make sure you have everything copied up to this point. Okay, we're going to do example 6. Okay, so example 6. Let's get this copied in here. Should be the last one on your note sheet. Oop, that's not it. There it is. Example 6. Sorry about that. So let's find the general and particular solutions to this kind of interesting differential equation. And it might not look that interesting. It looks pretty simple to start. But do you notice anything about the right side that's different from before? Maybe the fact that there are no x's on the right side, but there is a y. We haven't done anything with a y on the right side yet, and we'll see what happens when that's the case. It actually makes for a pretty interesting problem. All right, so we'll rewrite dy dx is equal to 3y. Okay, now step 1 is to get your y's on the left and your x's on the right. Okay, so if we divide by y, we could write this, and we multiply the dx up, we could write this as dy over y equals 3 dx, but I don't think this looks very nice. So we're going to rewrite this as 1 over y is equal to, 1 over y dy is equal to 3 dx. Okay, this looks a little bit better. All right, so now that we have everything separated, we're going to go ahead and integrate. Okay, so we'll go ahead and integrate here. Okay, so what do we take the derivative of to get 1 over y? What's the antiderivative of 1 over y? Well, that's ln absolute value x. We use absolute value because, we can't plug negatives in, and we don't know, we haven't specified any restrictions on what we can plug in for, what we can plug in for y. So we have to use absolute value. Okay, is equal to, and this will go to 3x plus c. Okay. So, we're at an interesting place here where before, all of our answers, we just had the y by itself, right? And now it's not. Okay, so I'm going to go ahead and solve that problem, get the y by itself. That's going to make life a lot easier. So we're not done just yet. We don't have the general solution yet. Okay, we'll have the general solution when we have y by itself. Okay, so let's go ahead and get the y by itself here. How do you undo ln? You undo it by making e the base, and they cancel out. So we make e the base for both sides. Okay, and so e ln cancel, and we get y equals e to the 3x plus c, which we could rewrite, thanks to exponent properties, as e to the 3x times e to the c. Okay, now let's think about this. We're taking a constant e and we're raising it to a power. That's a constant as well. Okay, a constant raised to a constant. Well, that's just a constant, right? That's just a constant. So we can simplify this. Okay, and this is where I know some of you are going to have questions, and that's okay. This is a constant raised to a constant, so we're going to rewrite it as just a constant. We're going to take this whole thing and we're going to make it a c. Okay, we're going to take this whole thing and make it a c, and we can make this look a little nicer. Okay, let's just write this as c e to the 3x. Okay, so it's kind of interesting, instead of having a plus c in our general solution, we have a times c, and there's nothing wrong with that. Okay, so our general solution is y is equal to c e to the 3x. Okay, I think the reason why an equation like this is so cool is, just looking at it, most people don't just look at it and go, oh, hey, an e is going to show up, but there it is. Okay, so let's do the particular solution now. So we did general in blue, and we'll finish out with the particular in pink. Okay, so we know y of 0 is equal to 1. Okay, so that means that 1 is y and 0 is x. So 1 is equal to c e to the 3 times 0. 3 times 0 is 0. E to the 0 is 1. So we get 1 is equal to c. So our particular solution is y equals 1e to the 3x. Not bad. Not bad. Okay. We'll give it a smiley face. So, one more thing, and I think this is going to really help. So we can take this process and we can make it much simpler. Okay, we can really um, turn this into a three-step process that's just a few words. So another way of thinking about solving these differential equations, or really anything where you're taking an integral and you have an initial condition, is separate. So separate your x's and y's, integrate, integrate both sides, okay, and then lastly solve for c. Solve for c. Okay, so we can take all of these steps, boil them down to separate, integrate, solve for c.